Hey y'all, welcome back to a long-awaited, long overdue episode of Science and Engineering in KSP. I'm your host, Andy Leonard, and I want to start off by apologizing for that long break. I think it was like a year and 3 months. Had a lot of stuff going on, school, work, stuff like that, and I just kind of fell out of it. So I do apologize for the break, but it did always kind of nag at me that I didn't come back and do that episode that I promised y'all at the end of last episode, where we tied together a bunch of the things that we had talked about, like propellant mass optimization combined with patched conics and stuff like that. So I wanted to come back and get in this episode where we do just that. We're going to plan a Munar mission today. And so there's 3 basic steps that we're going to need to do. First, we're going to have to figure out our delta V requirements using the patched conic approximation. And then we're going to have to build our payload and determine the propellant mass. And then we need to estimate the timing of the engine burns that we're going to have to do. So 3 basic steps, nothing too complicated here. So let's dive right into figuring out our delta V requirements. So, step 1, we got to figure out our delta V requirements. And to do that, we're going to have to do a patched conic analysis. And if you need a refresher on the patched conic analysis, check my last video, because I went through the process and explained it and drew diagrams and stuff. And so to do the patched conic analysis today, I wrote a pretty simple Python script, which I'm going to make available online for you guys to download and play with and make your own. And if you've never programmed before, do not worry, because number 1, Python is a super easy language to learn, and it's a great place to get started programming. And number 2, and more importantly, there's not really much actual programming going on in this script, okay? All we're doing is just stringing together basic calculations, stuff that we could do with a pencil and a paper and a calculator. The only difference is that we're going to let Python do it for us in a fraction of a second versus taking 20 minutes to write it all out. If you haven't worked with Python before, I recommend checking out the package Anaconda. That will give you everything you need to get started. And it's really great to mess around in Jupyter Notebook, but it's really flexible. So let's start talking about the script. First, we import NumPy. NumPy is a library that gives us access to a bunch of different mathematical functions that we'll need. Next, we declare our constants, stuff like the gravitational parameters and masses, because we're definitely going to need those. Then we figure out what the spheres of influence of Kerbin and the Moon are. Now we start our analysis by picking our departure orbit radius, or our initial radius about Kerbin, and so this is going to be your circular orbit radius, and so I picked 686,750 meters. You can set this to anything you want, but definitely don't go any lower than 670,000, because any lower than that, you are within Kerbin's atmosphere, which is no good, and anything lower than 600,000, you're within the surface of Kerbin, which is definitely not good, right? Next step is to pick a transfer orbit apoapse. So I set an apoapse to 12,240,000 meters, and I explain why in the comment here. But you can really set whatever you want to do, just kind of keep it around 12 million meters, plus or minus 500,000 meters, and see what happens. And then we figure out some of the parameters of this transfer orbit, like our semi-major axis, the velocity at periapse. This will be the velocity we hope to achieve just after our first burn. And then we go ahead and figure out some other things like the energy and the angular momentum. And then we pick lambda 1, which is the angle at moon arrival with respect to a line joining the centers of Kerbin and Moon. And if you're like me and have trouble visualizing this, again, check out my last video, because I drew it out and hopefully make this a little bit clearer what it is. Next, we go ahead and calculate some of the parameters of the patch condition. So this is just before we cross over into the Moon's sphere of influence. We're still in Kerbin's sphere of influence. So we figure out our radius and velocity, and our flight path angle, and the phase angle at the patch, because we'll need this to figure out where we burn. And then we figure out some other parameters like the semilatus rectum and the eccentricity, because we need those to figure out the true anomalies. And then we need those to figure out the eccentric anomalies, which we need to figure out the time of flight. and we need the time of flight to go here in our phase angle calculation, because this will be the phase angle that we burn at. And this is very, very important to know, right? Because if we pick the wrong phase angle, yeah, we'll have the right size orbit to get to the moon, but we could be on the opposite side of the moon's orbit from the moon and not get an encounter. And that wouldn't be good. So after we've done that, we turn our attention to just after the patch, so we're within Moon's sphere of influence now, and we figure out our velocity within Moon's sphere of influence, and we figure out some of the other orbital parameters, like this angle here, epsilon 2, the entry radius, which by definition is going to be the sphere of influence of the moon, mechanical energy, angular momentum, semilattice rectum, eccentricity, and we figure out finally what our moon periapse radius is. And so this is the only bit of actual programming here, very, very simple. So 92 and 93. We have a very simple if statement. So if our periapse radius is less than 200,000 meters, meaning if it's within the surface of the moon, we'll get an alert. So that tells you that your moon periapse radius is less than the moon's surface radius, and you need to adjust your entry angle. And so it's not super important to adjust that entry angle if you get this warning, because you can very easily correct for something like this if you're far out enough. But I just thought I'd throw this in here just to be safe. And so that concludes the patch conic analysis. Now we talk about the delta V requirements, and we figure out our delta V requirements simply by comparing those periapse velocities that we found, the periapse of the transfer orbit about Kerbin, and then the periapse velocity about the moon, and we compare those two circular velocities. And the punchline is that we find delta V for our first burn and delta V for our second burn by doing that. And so now at the end here we have just a couple of print statements to tell us what we found. So let's go ahead and run this. In Jupyter Notebook we hold shift, hit enter, and we see that to leave Kerbin we're going to have to burn 852.963 meters per second. We're going to have to burn at a phase angle of 124.781 degrees, but there's a little bit more to the story here, which we'll get into a little bit later. Our periapse altitude about the moon should be about 46,721 meters, and the delta V required to circularize about the moon is going to be 292.517 meters. So now that we have our delta V requirements, let's start building the spacecraft. So this here is my payload, and let's just go line by line. We've got a one-seater capsule here with a mass of 0.84 tons, which means it's got a mass of 840 kilograms. We need a power source, so we've got two solar panels here, the 2x3s, each of which has a mass of 17.5 kilograms, so times 2, that's 35 kilograms. And probably most importantly here, we've got the Kerbal engineering system, which has a mass of only 5 kilograms, but it's what's going to be able to tell us what our phase angle is, and it's an absolutely essential part to have if you want to math your way through Kerbal Space Program. Next we need power storage, so we've got the batteries, each of which has a mass of 5 kilograms, so that's 10 altogether. And then we have the Terrier engine here, the LV909, with a mass of 500 kilograms. Next we got the fuel tank, and the dry mass of the fuel tank, the first number when you click your middle mouse button, is 125 kilograms, and that's the number that we're going to focus on for our first calculations here, because that's going to be our dry mass or our empty mass where there's no propellant in there whatsoever. Finally, we want an antenna just for safety, and that's going to round us out an additional 5 kilograms. So notice I don't have a parachute or heat shield or decouplers or anything like that. Whichever Kerbal draws the short straw is just going to hang out around the moon for all eternity or until we can get a rescue out to him. And also notice I'm not worried about the launch vehicle or anything. I trust you all can get to orbit, and if not, it's no problem. There's a wealth of great tutorials out there for you to check out, but all of the analysis we're doing in this episode is purely space flight and not atmospheric, so we're not going to worry about that. So let's switch over and start talking about our propellant mass calculations. Next, we're going to want to open up a spreadsheet, and I'm using Google Sheets here, which, as with the code, I will make available for y'all online. So over here off to the left, I've itemized the spacecraft mass by subsystem to wind up with a total dry mass, that's mass without any kind of propellant, of 1,520 kilograms. And then over here off to the right, I've got the delta V values we're going to need to achieve in each separate burn. I've got the specific impulse of the Terrier engine in vacuum, and I've got G0. So if you remember back to the video on the rocket equation, you know why I need these two values here. So rearranging the rocket equation, we get that the full mass, or the mass before we initiate burn 2, is going to be E to the delta V2 divided by G0 ISP times the dry mass. And then we get 1,657 kilograms, which means when we take that minus the dry mass, we get the mass of the propellant consumed in burn 2 is 137 kilograms. And then we basically repeat the process, right? So we do E to the delta V1 divided by G0 ISP multiplied by the full mass, or rather the empty mass, which is going to be the full mass of burn 2, right? So that becomes the empty mass of burn 1. And then we find that the mass of propellant we'll have to use in burn 1 is 475 kilograms. So we're able to figure out the total propellant that we need. And by the way, remember, propellant is fuel and oxidizer, not just fuel. That's why we want to be specific in calling it propellant. We figured out the total propellant mass is going to be 612 kilograms, which means the mass of the propellant plus tank is going to be 737 kilograms, which means the total mass that we're going to start with is 2,132 kilograms. But if you remember, when we've tried to tweak the propellant before, there's a little bit of a wrinkle here. So let's switch back to KSP and talk about it. So if we get up in here, up in our tweakables menu, we right click on the tank and we can specify the liquid fuel and oxidizer. Remember that there's only a set amount of, I guess, discretization that you can control your fuel mass with and your oxidizer mass with. And so it looks like it goes, for this one, it goes in units of, it goes in 9 unit increments. I think the unit they use is some sort of volume measure, but anyway, it translates out to mass. So if I set my sliders down here, and for this case, you want to keep your fuel and oxidizer in equal proportions here, or at least equal proportions here visually, just so they'll burn at the same time. If we look, we've got a mass here of 2,120, which if we go back and if we look at our mass, our fuel mass, I think the fuel mass, or the propellant mass that we were going for was like 2130. So this is too little propellant, right? And so if we increment it by one little notch here, we have extra mass. So 2,220 kilograms. So since we cannot use this this level here, this 2120, we're going to have to use the 2220. Okay, and that's going to change our math up a bit. So we're going to head back to the spreadsheet and redo some calculations. So now that we know that we are restricted to an actual starting mass of 2,220 kilograms, we can figure out what our actual propellant masses are going to have to be. So we do that by rearranging the rocket equation again to find the mass after burn 1 is going to be the actual starting mass divided by E to the delta V over G0 ISP. And we figure out that we're going to use 494.7 kilograms of propellant in burn 1. And doing the same thing for burn 2, we figure out that we use 142.9 kilograms of propellant in burn 2. And so if we compare these to to our original assumption, we find there's not too much difference, right? So we've got 137 versus 142 kilograms, and then we've got 475 versus 494 kilograms. So not too much, but it is significant enough that we do have to account for it. and we'll have a little bit of a margin left over in case we make mistakes. So that's good. Now what we want to do is we need to figure out the time of each of these burns, how long we're going to need to burn for to achieve the delta V we want. And to do that, we're going to need to get the maximum thrust of the Terrier in vacuum, which is 60 kilonewtons or 60,000 newtons. Let's just assume that we're going to be at 100% throttle for each burn. And then what we're going to want to do is we'll take the propellant mass, multiply it by G0 ISP, and divide it by the thrust. And if it's not apparent why this works out the way it does, I invite you to do some dimensional analysis and see if you end up with seconds. And then so we do that for burn 1 and for burn 2, and we figure out we're going to have to burn for 27.9 seconds in burn 1 and 8 seconds in burn 2. But now, importantly, we need to find the phase angle, because remember what I said when we did the Python script, the phase angle that it spits out is not the whole story. So there's kind of an analogy. There's kind of an analogy with maneuver nodes here, right? Because you know that you have to burn kind of half before and half after a maneuver. You can't just burn on the maneuver, or you're not going to get the results you need. So it kind of works the same with phase angles. So what we're going to do is we're going to plug in the phase angle that we got from the Python script. We're going to plug in some other constants. We're going to figure out the angular velocity of the spacecraft around the Earth, or around Kerbin, sorry, and the angular velocity of the Moon about Kerbin as well. And what we're going to do is we're going to take the original phase angle, and then we're going to add the difference in those two angular velocities, which up here we've converted to degrees per second, and we're going to multiply that by half the burn time. And so when we do that, we see that we'll have to initiate the burn at 127.38 degrees. So yeah, that's pretty much all the math that we have to do. Let's switch back to KSP and finally see how we did. Alright, so here we are in orbit. I have the game paused because there's something I want to talk about real quick. So the timing for this burn, we know, is going to be 27.9 seconds, or 28 seconds. We just round up and call it that. And ideally, I would like to use a stopwatch to clock this, just because it just feels more natural to me. But if you're like me, maybe your computer isn't 100% optimized for gaming, and because I can say that my computer is certainly not optimized for gaming and then capturing that game at the same time. So if you've got a good rig, then go ahead and use the stopwatch, and you should have time pass in the game as expected. But if your computer isn't quite that up to snuff, and no shame in that, because same thing happens to me, we're going to go ahead and go by the mission clock up here. Okay, and so we have the rendezvous window open. We see that the phase angle is 134 degrees, and it's going to count down. So as soon as I unpause it, it's going to start going down. And what we want to do is we want to make sure SAS is on. We want to point prograde and lock our steering there. And we'll go ahead and, since I haven't activated the engine yet, I can kick the throttle up to 100 preliminarily. And yeah, so Jeb is looking out the capsule, taking one last look at Kerbin, because he will not be back for a little while, because he only has just enough fuel to get to the moon. So we're coming up on that magic number of 127, and here we go. So that's 32, 1 hour, 32 minutes, 32 seconds, 28-second burn. We should be killing our engines at 133. And now we just kind of play the waiting game. And yeah, see that little yellow flicker there? I think that means that the game is kind of struggling to have time go in real life. But at any rate, we made it. We completed the burn. Let's see how we did on the map screen. I noticed that the change in velocity here is a little bit higher than it should be. I think we should have been aiming for 3120 meters per second. But we've got an open orbit, so that's encouraging. And we do have an encounter with the moon. Unfortunately, it appears that we are going to impact the moon, but that's okay. The patch conic approximation is just that. It's an approximation, and it is just about the definition of the phrase close enough for government work. So what we're going to do is we're going to point retrograde, and we're going to try and get our periaps about the moon up to that magic 45 number we had, because that was a nice round-ish number. So 41, 44, 46, it's fine. So we'll go ahead and warp there. And Jeb is having fun on his way out there. I'm not sure if anybody has told him yet that he doesn't have enough fuel to come back. But I guess he'll figure it out. Pretty funny story about not having enough fuel to come back. So the Apollo 10 astronauts, the mission just before the first moon landing, the Apollo 10 astronauts took the command service module and the lunar module out to lunar orbit to just kind of test it out. So they had already taken the command service module out there on Apollo 8, but they hadn't tested the lander out yet. And so the idea was to take the lander and just kind of fly it over the moon and see how it performed. And so those guys totally probably could have attempted a landing, but they definitely would not have had enough fuel to make it back into lunar orbit. So you kind of have to wonder if they had the thought, just the fleeting thought of like, screw it, it's a pretty baller way to die, dying on the moon. I mean, I know, shoot, I would. I mean, I would do what Jeb's doing here, like, provided that I had enough snacks to last me the rest of my natural life. Like, yeah, I'll just hang out in lunar orbit, and like that'll be my thing. So we're coming up on periaps here. We're pointed retrograde, and we're going to wait until we are 4 seconds out, and then we will burn for 8 seconds to close our orbit about the moon here. So that's 5, 4, 1, 2, 3, 4, 5, 6, 7, 8. And so, yeah. Oh. Looks like we overdid it just a tiny bit. Ah, well. So yeah, thank you so much for watching. I hope you had fun watching it. I had fun making it. I do apologize again for the hiatus. I can't guarantee when I'll have a new video up, but probably be less than a year. And yeah, it may or may not be KSP. I've got a couple of non-KSP ideas kind of floating around. Or it might be KSP. There's a lot of cool stuff we haven't done yet. We haven't done interplanetary transfers, which is where patched conics really starts to shine as an analysis method. I don't know if I've told you guys this, but patched conics from Kerbin to Moon, or from the Earth to the Moon, pretty imperfect, I think, as you've seen. But it works a little bit better when we're talking about going from planet to planet. We could talk about flybys, we could talk about asteroids, basically whatever. So there's it's a lot of room for fun stuff to do. But yeah, anyway, thanks again for watching. See you next time. So yeah, real quick, the reason that last circularization burn didn't work out was because obviously we changed our orbit. We didn't have that same incoming velocity, and we wouldn't have that same velocity at periaps as we had calculated, so that's why it wasn't an 8-second burn. See ya.